This is Lab 7, Extension 2.3 and 2.4. If you have not yet completed the questions or the previous activities, please pause your video and do that now. I'll make a note about question 2.5. It's a little tricky. You're asked to verify this equation right here, and there are a couple of ways to do it. One way is to just say, okay, well, the equivalent resistance, that's what we measured when we put all three in parallel. You can do 1 divided by that value. You're going to get a decimal. And you can see it, does that equal 1 over R1 plus 1 over R2? And then all these were close to 51 plus 1 over R3. Now notice if R1, R2, and R3 are all the same, if they're all 51 ohms or close to 51 ohms, this side of the equation is going to equal 3 divided by 51. If you have 3 over 51 and 1 over the equivalent, if you invert both sides, then you're going to have the equivalent resistance is equal to 51 divided by 3. That's maybe an easier way to do that. We're ready for these right here. So I've got two resistors. I've got one of these is a 75 and one is a 22. How do we know? We can look at the color codes. And I'll take a look at this one. This one right here. This has a color code of purple, red, black, gold. So the purple is 7, brown is 1, black is 0. 71 times 10 to the 0 is 10 to the 0 is 1, so 71. And then the gold band means give or take 5% of that value. Here I've got a red, red, black, gold, brown. Red, red is 2, 2, black is 0. 220 times gold is going to be 10 to the minus 1, or 1/10 is my multiplier. So a tenth of 220, 1/10 of 220 is going to be 22 ohms. And then the brown means give or take 1%. So this one, the tolerance is pretty close. This one is give or take 5%. Let's go ahead and see what our multimeter says. So I'm going to turn my multimeter on. I'm putting it on the lowest setting for resistance. Here's our omega sign. It says overload right now because there's quite a large resistance between the two leads. They're not connecting each other, and so it's not measuring any current. And I'm going to take my 75 ohm, or at least that's what the color band says. I'm going to pinch this together and try to get really good contact with the metal tips. Push them in there, and I'm going to take a look, and it says 50.6, and that makes me wonder if I said that was purple. Well, you know what? I take a look at it again. These colors are a little faint. I'm going to say maybe that isn't purple. Maybe that's a green. I'm going to have to go in my bag and grab another one. I grabbed a different resistor, and sure enough, that first band looks a little bit more purple than the last one did. Let's see what the multimeter tells us. I'm going to pinch one side, pinch the other side, and now I'm getting a reading of 75.1. So that's a little higher than I thought it was going to be. And nope, 75.3. And that's why. Because that second band is green and it's not a brown one. So it's supposed to be a 75 ohm resistor. Perfect. So 75 point, let me take another look at that. 75.2 or 0.1 even, 75.1 ohms. That's going to be R4. Now let's take this other one and I'll pinch it. Red's a lot easier to see, so I'm pretty confident this is a 2-2. And push this into here, and we get a value of 22.0 ohms for R5. The nice thing about a breadboard is it can hold resistors together without me having to do that physically with my hands or with wires. Each of these rows, here's a row right here, each of these little slots is connected to the other slots in the same row. So this one is plugged into row 8, but so is this one right here. So these two ends are both held together by row 8. And likewise, these are held together by row, looks like 16. They're held together. So I've got this is connected to this end, and this end is connected to that end. And I'm ready to measure the resistance of these three in series with each other. I'm going to hold my N1 end of the ohm meter, or my multimeter there. And I'm getting a reading now. It's stabilized at 147.6. 147 now it's at 147.5.6, so it's fluctuating a little bit on that tenths of an ohm. That's our value for the three in series. Now we've got our three resistors no longer connected end to end to end, but we have the ends of all three of their ends are in row 1, so they're all connected together, and the other three ends are connected are all in row 8, so they're all connected together through that row. So I'm ready to measure the resistance of these three resistors in parallel. Now here's a question for you. Let's think about our intuition. Here's a 22. This one's our 75, and this one's our 51. If I just had this one by itself, the smallest one, the 22 ohm, well, its resistance I expect to be 22.0 ohms. But I've added another one in parallel to it. What's that going to do to the resistance of that network if I add a resistor in parallel, offering a parallel path? I expect it to go down, to drop below 22 ohms, even though it has a resistance of, in this case, 75 ohms. And then I add a third one, I'd expect it to drop even further. So adding these resistors, let's see if that's right. So, because I'm making those extra pathways for current to flow, I'm going to put one of my leads on the row 8, and I'll put the other one on row 1 and press them into there, and I'm getting a reading of 12 point, I kind of lost touch with it. Okay. So the tricky part of this is these tips are really small, and I'm trying to push them into the tips, and sometimes I'm pushing the plastic. Here we go. 12.8 ohms. 12.8 ohms for the combination of these three resistors, R1, R4, and R5 in parallel. If you've not yet filled out these questions, go ahead and fill out these questions. There is a little bit of math. Here's another suggestion. On your calculators, you have an x to the minus 1 button, and that's kind of a convenient way to invert your values. So you wouldn't have to type in 1 divided by 22 and 1 divided by 75. You could just type in 22, hit that x to the minus 1 button, and it inverts it for you. So you can type in those resistance values of your R4, your R5, and your R1. Type each one in 51, hit the x to the minus 1. 22, x to the minus 1. 75, x to the minus 1. Hitting plus in between, so you're going plus. And then when you hit equals, you're going to get a decimal, a very small number, because you just added 1 22nd plus 1 51st plus 1 75th. So the already small decimals, you added up together some small decimals. It's going to be less than 1 point something something. But now you're going to want to invert that. So you can go and hit answer, hit the x to the minus 1 button again, and that'll flip this equation over, and you're going to get the equivalent resistance. So that's a good way to check it here. Just kind of show your work what you're substituting in using that equation, and then see how well that equation holds up. This is a way that you can solve now networks of resistors where some are connected in series to others that are in, and those series are in parallel with that one, and all three of these, that combination is in series with this one. And it kind of shows you how to kind of solve it like a puzzle. Well, these two are in series, so I'm going to add those up. These two are in parallel. I'm going to add those up using the other rule. And now this, whatever that equivalent resistance was, I'm going to add to this one in series. And so you're going to just gradually work your way through. This equation here looks a little funny. It's just another way of using that one, the inverse, adding up the inverses. If you find a common denominator, it'll put in there. So you don't have to use this. You can just use the equation on the other side. we're ready for this monster equation. So R1 is going to be our bigger resistor. That's going to be our 51 ohm resistor. And R2, oh, the other way around. R1 is going to be a smaller one. R1 is going to be a 22.0 ohm resistor. And R2 is going to be the bigger one, 51 ohm resistor. I've got that set up right here. Now with the breadboard, the way that it works is that these two are held together because they're in the same row. And so these are in series. This is a 22 together with a 51. And those are in parallel with this one down here, which is a 22 with a red. So these two in series are in parallel with that one. Now these all three are in the same row, this end, so that's in series with this one right here. On the other side of the breadboard, I have these two resistors that their ends are in the same row, so these are in parallel, and both of these are 51 ohm resistors down here. And now I've connected this side of the breadboard to this side with these jumper cables right there. So these are just wires that are connecting this, that connects this row to this row where the other resistors are. So where's my point A? Where's my point B? Well, my point A is right here in the middle of this wire. I can't access it. It's wrapped up. But really, I can go to any piece of metal that's touching it. So I can make my point A here or here, and I can make my point B any piece of metal that's on that side of it. And that's what I'll do to measure the equivalent resistance of this circuit. Here we go. Pinch this one in here. And if I just touch it lightly, I don't get a good reading. I'm going to try to push it, the metal against the metal. And my ohm meter is settled down around 16.3. 16.3. I actually just went down to 0.2. 16 point. No, now it went down to 1, so it's drifting a little bit downward. 16.1. And it just went to 15.9. I wonder why it's drifting. I don't know. And so it looks like it's somewhere, let's just say 16.0 ohms, give or take a few tenths, because as I kept holding on to it, it drifted all the way down to 15.7. So I'm going to let go of it and try to read it again, starting anew. And now I get, oh, it starts right at 15.8. So maybe I just have a better connection now. And it's not, oh, it just went to 15.7. Where is this going to end up? Is it still drifting downward? No. 15.7 ohms. That's my final answer. 15.7 ohms. And so this is our equivalent resistance. I kind of spilled the beans. Now it says like calculate it, show your calculations, and then step 3 was to test it. So if now your goal is to now go back and see if you find the equivalent resistance of all of these, starting first with the two in series, add those up in series, then take the equivalent of that with this one that's in parallel, get the equivalent resistance there. Now you've got that in series with this one. These two are in parallel, add that up, and then you've got all of this up here, whatever the equivalent was up there, in parallel with the equivalent there. So you have lots of little steps. Add that up and see if you don't get an answer pretty close to 15.7 ohms.